Good morning, everybody. My name's Danny Williams, and thank you for everybody attending today's webinar on detailed PCB thermal modeling with thermal territories. If you guys are currently listening right now via phone, I would recommend you guys turn on your actual computer audio because what we're going to be listening to today is going to be actually playing through your computer speakers. And please keep in mind that our video in webinar in total is going to be recorded, so you will be receiving a notification in the email after the fact in case you want to check this out later. And we're also going to be having a Q&A at the very end. So if you guys have any questions that come up during today's webinar, though, there is a questions option so that you guys can send us a question if you have it. So without further ado, please sit back and enjoy.
Welcome to today's presentation on detailed PCB thermal modeling with thermal territories. Today's presentation will discuss various methods to thermally modeling printed circuit boards, and will finish with the latest methodology known as thermal territories. For today's agenda, I will begin by discussing the motivation for the various PCB modeling approaches. As we cover each method, I will discuss in terms of what, when, why, and how. My hope is that if you're new to thermally modeling PCBs, you will gain at least an introductory understanding to the pros and cons of each method and how you might go about implementing them in your design process. The first method we will cover is effective thermal conductivities. Here we will introduce the concept of modeling a PCB as either lumped or detailed. Next, we will cover image processing, which allows the PCB to be represented as many areas of different thermal conductivities. The final method we will discuss is explicit trace. I'll provide an overview of the historical method of representing explicit traces and introduce you to two methods of capturing explicit traces in Flotherm XT, one of which is thermal territories. We'll finish with the thermal territory example using the BeagleBone blackboard. The motivation or goal with thermal analysis of PCBs is to develop accurate or accurate enough predictive models through scalable and repeatable processes. Thermal analysis provides benefit during each phase of the design process, and designs change quickly. Thermal analysis is only beneficial if it can keep pace with the other design flows that leverage existing data. Thermal models can be built and updated more quickly if it can import or otherwise leverage data from other design flows. Within the time constraints of the workflow, again, for thermal analysis of PCBs and of electronics in general, analysis provides the most benefit if it can provide insight during each phase of the design flow. For PCBs, the design evolves from concept, where PCBs are modeled using more assumptions to uncover any useful trends or determine feasibility of a design, through verification, where the final thermal analysis and design are performed prior to prototyping and testing. The first method we will discuss is effective thermal conductivities. This is where the copper distribution in the PCB is represented as a region or multiple regions of effective orthotropic conductivities. This method is used early in the design process or in system-level models where there may be multiple PCBs in the model, and forced convection models. Some of the reasons for using this method are due to the fact that there isn't much information that will allow for a more detailed model to be created. Or it may be that modeling the detailed PCB traces would result in a model that is too computationally expensive. Thermal analysis involves balancing accuracy with analysis time. It could be that the PCB isn't a significant heat transfer path. In the example shown, the critical components are heat sinked and a small percentage of heat is rejected through the PCB. It wouldn't be wrong to model the PCB in more detail, but it typically wouldn't result in a more accurate thermal model. So how are effective thermal conductivities implemented? The first approach is lumped, where the PCB is modeled as a single block with an orthotropic conductivity. One approach is to use the percent conductor by volume. Using conduction in series and parallel calculations, the through plane and in-plane conductivities are determined. 10 to 20% conductor by volume is a reasonable first guess. This modeling approach is used early in a design process, typically for trend analysis. The next approach is known as detailed. In this approach, the individual trace layers are represented with an effective thermal conductivity, which is a weighting of the areas of the conductor and dielectric against the total area. I would say this is possibly still the most widely used method in PCB thermal analysis. Let's take a look at how the in-plane and through-plane conductivities vary with percent conductor by volume. The in-plane varies essentially linearly with percent conductor. The through-plane changes very little with percent conductor and only gets up to around 6 watts per meter Kelvin when the percent conductor, in this case copper, is at 95%, particularly in the areas of 10 to 20% copper. If there are thermal vias present, the through-plane conductivity should be adjusted in the areas where the vias are located. As an example, consider a heated component on a vertical PCB in natural convection. The graph shows a plot of the thermal resistance, where the thermal resistance is defined as the component temperature rise over ambient divided by the power dissipation. So the plot is showing thermal resistance versus percent conductor by volume. The thermal resistance varies from around 5.5 to 4 in the area identified as the typical assumption of percent conductor by volume of 10 to 20%. As the percent conductor increases, the relative change in thermal resistance decreases. This example is meant to represent what you might hope to achieve with this modeling approach, which could be a preliminary assessment of temperatures and a trend as input variables change. I did one other study where I compared the lumped approach versus the detailed approach. The table outlines the PCB construction and is the default stack-up in Flotherm's FlowEDA bridge. If you do the math, multiplying the thickness of each layer with the copper coverage, adding those up and dividing by the PCB thickness, this PCB has a percent conductor by volume of 2.8%. Not much copper. Many PCBs today require multiple power and ground planes and can't be routed on 2 signal layers. So this represents a PCB with not very many components. The lumped approach predicts a component temperature of about 52 versus 39 for the detailed approach. Modeling each individual layer allows the heat from the component to spread much more efficiently, and as a result, the predicted temperature is much lower. And I think we see such a huge difference in this case because the amount of copper in this board is so low. The next method for PCB thermal modeling is based on image processing. This method still involves discrete regions of effective conductivities but allows for copper distribution within a layer. For example, if we pixelate an image, we get larger areas with multiple shades of gray. Each shade of gray would represent a different orthotropic conductivity. This method would be used after PCB routing, which would provide the images for each layer, and could be used in a system-level model when increased accuracy is desired. Why would you use image processing? Well, it is a scalable and repeatable process, and it leverages existing data, and it's computationally efficient. It's efficient in terms of the required mesh, and as such would be suitable for larger system-level models. And no MCAD is required, as it is based on images and not MCAD models. There are 2 approaches in Flotherm for processing images. The first approach is through Flotherm's FlowEDA bridge. When CCE, ODB++, or FlowEDA files are imported, the layer images are imported and can be processed in the dialog shown. The CCE file is an expedition file. ODB++ files can be exported by most, if not all, PCB routing tools, and the FlowEDA file is a Flotherm-based file generated from plugins for Expedition, BoardStation, Allegro, APD, and CR5000. The interface shown allows the image to be processed into a number of orthotropic thermal conductivity patches and requires no specialized image processing knowledge. Flotherm can also process images through automation. An Excel file provided with the Flotherm installation will process image files to create a detailed representation of the trace layout. The Excel VBA-based script converts the images to geometry using the FlowXML file format. As an example, I'm showing a detailed flip chip BGA, which is an example that's installed along with Flotherm. The traces are represented using the PowerMap Smart part within Flotherm. Entire Flotherm models can be created outside of the software using the FlowXML file format. What if you didn't have Flotherm, but you were interested in converting images to geometry and thermal properties without knowing how to process images? The next few slides will cover one approach that could be taken. So we'll start with the layout image. Consider a small area in that image, or a patch, for consideration. An image made up of only black and white pixels. This image can be converted, I use IrfanView, to an ASCII PBM file. This file represents the image as an array of ones and zeros. 1 represents black pixels, or the conductor in our PCB, and zeros represent the white pixels, or the dielectric. The first step involves calculating the effective thermal conductivity for each row and column. If we look at the upper row, we see that the conductivity is 0.3, the conductivity of FR4. A few rows down, we have a row that is all copper and has a conductivity of 385. The calculation is based on conduction in series. The 1 and 0 subscripts in the equation refer to the values in the file, or the color of the pixel. The next step is to average the effective conductivities. In the z direction, the conductivity is the area-weighted average of the pixels. The result is the 3 conductivities, one for each coordinate direction. Image processing shown here or within Flotherm considers the conductivity of the black pixels within a patch and not simply the number of black pixels. The last method for representing the traces in a thermal model of a PCB is explicit trace. This involves the trace being represented as explicit geometry and not effective thermal conductivities. Like image processing, this method would only be used after PCB routing, later in the design process. This method would provide the most accuracy over any of the other methods discussed. When there's less copper in the PCB, for instance for a detailed IC characterization, this approach would be recommended. This method is used in situations where explicit conduction paths are required for accuracy, or to model Joule heating. Before we discuss the options available within Flotherm XD, let's discuss how it was done back in the olden days. The first step would be to obtain 2D drawings. Certainly we could create the solid geometry ourselves if we have skills and time. This process discusses how data could be leveraged to shorten the design process. So after we have the 2D data, it needs to be converted to 3D CAD through extruding the sketch into a third dimension. Issues with this process are it can take a long time, and each time it will be a little bit different than the previous. A certain degree of MCAD skills are required. If the layout changes, the entire process needs to be done again. Once individual 2D layers need to be connected with vias, the process becomes significantly more challenging. Because of these challenges and others, this process wasn't used very often. Flotherm XT offers 2 methods for processing trace information via CCE or ODB++ into 3D CAD data and a Flotherm XT model with no specialized skills. The first method is discrete net. Any net marked for explicit representation in the FlowDA bridge is converted to solid geometry. This is especially useful for Joule heating analysis where the trace is carrying a current that generates heat. The latest method for modeling explicit traces is with thermal territories. Rather than defining the region using the net, it is associated with a component on the PCB. Once the component is enabled, we have choices to determine how much copper we want to resolve explicitly. This is controlled through 2 settings. The first setting is the inflation size. So that's the distance away from the component where the copper will be resolved explicitly. The next setting is the depth to layer. How many layers, conducting layers within the board, should we resolve explicitly? The inflation size is shown around the component with the green border. Those components with the component territory enabled are converted to solid geometry. This is especially useful for capturing conduction paths near components. Let's take a more detailed look at thermal territories through an example. The BeagleBone blackboard is simulated in natural convection. Though I'm showing a number of components on the board, the only component included in the analysis was a detailed QFN package. The study will explore the effect of inflation distance and layer depth of the thermal territory on the predicted junction temperature. Areas outside of the thermal territory are modeled as detailed. I also modeled the PCB as lumped or compact and detailed for comparison. Here we're looking at the PCB stack up and Flotherm XT's calculation for percent coverage. The compact representation predicted a junction temperature of 56.7 and the detailed a temperature of 54.4. In this example, the surface temperature plot shows the PCB temperature distribution is very similar. My legend is based on a maximum temperature of 70 degrees, and this is to be consistent with the plots on the next page. There's a lot of information to process on this slide, and I apologize. For my study, I considered two inflation sizes, 1 millimeter, shown in the upper row of surface plots, and 5 millimeters, shown in the lower row. The images as we move from left to right show results with increasing layer depth for the thermal territory. The image on the upper left represents the least amount of explicit copper, and the lower right the most explicit copper. I have included images of the explicit copper in each Flotherm XT model. So the images on the left, where the thermal territory depth was to layer 2, shows a top view of the explicit copper. The remaining images are a bottom view of the copper, so we can see what copper was added for each design scenario. Each surface temperature plot is a top view of the PCB surface. I considered layer depths of 2, 3, 4, and 6, where 6 is through the entire board. The results show that the PCB temperature and the QFN junction temperature increase as the layer depth increases. So as we move from left to right, we can see the temperatures are increasing. The results don't change as much with inflation distance of 1 and 5 millimeters, so the upper row images are very similar to the images in the lower row. I've summarized the results further in the next slide. In this chart, the lighter blue bars represent an inflation distance of 1 millimeter, and the darker blue bars a distance of 5 millimeters. Each pairing represents a different layer depth. So we go from 2 to 6, where 6 is the bottom layer. The biggest difference in temperatures comes when the layer depth goes from 4 to 6. And we can see in the images I have with copper there that we're adding quite a bit of copper between those two design scenarios. The amount of copper resolved discretely between layer 3 and 4 wasn't substantial, and the temperatures didn't change significantly. In this example, the predicted temperatures are less sensitive to inflation distance, though I only considered inflation distances of 1 millimeter and 5 millimeters, and I didn't include any neighboring heat dissipating components. This technology is fairly new and it's difficult to make any concrete recommendations on what inflation distance is sufficient or what the layer depth should be. If I had to say, I would start with 1 millimeter inflation and have the thermal territory extend through the board. At least that's what these results are telling me. The advantage of this method, besides providing the most accuracy as the traces are detailed, is that it can be changed easily and quickly. Never before has it been so easy to capture explicit PCB traces in a thermal model. That concludes the topics we set out to cover. Thank you very much for attending. In summary, we discussed three methods for the thermal modeling of printed circuit boards. We discussed how image processing can be used to model copper distribution, either through effective thermal conductivities or through explicit traces via Flotherm's PowerMath SmartPart and scripting. 3 methods for modeling discrete traces were shown, one based on image processing I just mentioned, and 2 based on methods found in Flotherm XT, which are discrete net and thermal territories. The right choice comes down to what information you have available, which often depends on where you are in the design process. And how much time do you have? And how accurate do you need the analysis to be? Many choices are decided through balancing predictive accuracy with computational expense.
All right. Well, thank you for everybody sitting here and watching today's webinar. We do have a couple questions that I will go ahead and ask. We have Richard Azaki on the line, who was our senior AE, to help us answer a couple of those. Richard, are you there?
Yeah, hey Danny.
Hi. All righty. So one of the first questions that we have today after going through today's webinar was, could we use the territories approach for the whole PCB?
Yes, potentially you could. Absolutely, there's nothing stopping you from doing that. However, you know, depending on the complexity of the board, you are going to have a lot of detail, and realistically, I think you're probably going to run out of mesh. And I don't know how much more accuracy it's going to add. So it's really about balancing simulation time with simulation accuracy, and I think that's probably maybe a bit overboard.
Okay, gotcha. And our second question is, can a voltage drop analysis be performed on a PCB trace?
Uh, the short answer is yes. Yeah. So if you actually import a net using that explicit territories approach, then you actually have the copper geometry, you know, where the components are joined together, or maybe you've got like a power plane you want to analyze. So once you've imported the geometry, you can apply electrical boundary conditions, voltages and currents on all the pads, and understand what the voltage drop is, as long as you have that geometry. So yeah.
Okay. All right, and one of the last questions that we have is, what PCB interchange formats does Flotherm support?
Yeah, so we saw on the screen a little bit earlier, so there is CCE, which is from Expedition. That's a Mentor Graphics PCB tool. The most common by far is ODB++. That's kind of like a step file for PCBs. Almost all tools can export that. There is also a competing standard called IPC 2581B. That's very similar to ODB++, but it's an open file format. So it's kind of like a SAT file maybe. So yeah, and then there's a couple of others, but really I think ODB++ is the main one that people should be aiming to import into Flowtherm, simply because it's the most common.
Gotcha. Okay, cool. Well, that seems to be all the questions that we have today, so thank you for helping with that, Richard. But everybody else who's on the line, please expect in your inbox to have a link to the recording of today's webinar, and we're going to have another one coming up, the last in our series, in a couple weeks, so we look forward to seeing you guys again. But I hope that you guys have a great rest of your day, and thanks again for attending. Bye-bye.